So our next speaker is Frank Ueda. He's going to talk about Project Loon, a project that we have all heard a lot about. So he joined Loon in 2019 as a staff software engineer. He's now working on network infrastructure at Google. So he said he cannot talk about what happened to Project Loon, so please don't ask him about that. Okay. Thanks.
All right. All right, folks. Hello, everyone. My name is Frank Ueda, and it's my privilege today to tell you about Loon's network. In addition to all the co-authors listed here, I'm honored to present this work on behalf of a huge team of folks who spent a long time working on this project. And so I'll be very happy to take your questions at the end of my talk or any time during the breaks around the conference, but I should note, as was mentioned, that I'm here solely to discuss the technical parts of Loon. So during this talk, I'm going to tell you about Loon's approach to serving unconnected users via balloons in the stratosphere, how we connected these balloons together using highly directional steerable radios, and then how we utilized the novel Temporal Spatial SDN, or Temporal Spatial Software-Defined Network, which made predictions about the physical environment to dynamically configure those radios to connect into a moving mesh network to backhaul data. Finally, I'm going to share a few insights about how modeling our physical environment improved the performance of the network, and how network telemetry actually helped improve our models of the physical world. I'm only going to have time to touch on just a very few highlights from this project, but you can find me offline, and you can find many more details in the paper. So let me start off just by giving a little bit of background about Loon and our mission. So Loon started as an experiment inside of Google X, Google's Moonshot Lab, around 2011. The team sought to make the world a better place by extending internet connectivity to billions who lack it worldwide, by redesigning the essential components of a cell phone tower to be carried 20 kilometers up into the sky and rest in the stratosphere. So Loon was publicly announced externally in 2013, and in the following 8 years, it took this idea from a crazy science experiment to an actual production network and business that helped mobile network operators expand their coverage to underserved areas, supplement existing networks, and also provide expedient coverage after natural disasters. This was made possible by countless technical breakthroughs and advances in balloon sciences and other engineering that I'm not going to have time to talk about today. Ultimately, Loon was shut down in 2021, but during its operation was able to serve hundreds of thousands of unique users across 3 continents, both in disaster recovery and commercial contexts. So maybe to start off, we should talk about why Loon's approach was needed. So it turns out that the population that's not well served by traditional telcos is typically these folks live in outlying areas with low population density, often with geographical features that make traditional cellular networks perform poorly. So given the high per-user deployment costs of terrestrial networks and the limited potential revenue opportunity, telecom operators have few incentives to deploy existing solutions in these areas. And so for these users, this ongoing lack of internet access perpetuates and even widens the digital divide. So Loon's approach was to provide 4G connectivity directly to users' phones from base stations that are floating in the stratosphere. Now, for a long time, the stratosphere has been considered too hostile for large operations due to extreme conditions. However, its proximity is really attractive, as it opens up significant opportunities, in particular, our ability to go directly to handset. This altitude also changes the cost calculus of providing service to rural areas, allowing between 100 and 200 times greater coverage area per base station than a traditional terrestrial-based tower. Using the 4G access layer allowed us to partner with existing mobile network operators, and then it allowed us just to ride the momentum behind cheap, inexpensive, ubiquitous mobile phones. Now, building and operating a network in the stratosphere was a daunting challenge, and so Loon took a move quickly approach where we launched systems with known limitations and then tried to iterate. Now, if you want to run a base station from the stratosphere, you're ultimately going to need 3 things. You need position over your users, you need sustainable power, and you need backhaul. So with respect to position, Loon's balloons could autonomously navigate around the world by riding wind currents in the stratosphere. They could stay aloft for hundreds of days at a time at temperatures that reach minus 90 degrees Celsius. Further, the balloons could actually cluster together into teams or flocks that would provide sustained coverage over an area. With respect to power, our balloons generate their own power using solar panels, and they store the excess into batteries on board the balloons. Notably, our balloons in the latest generations didn't have enough battery capacity to actually run the communications payload the entire night. And so I'll talk about that a little bit later. That posed some interesting challenges. So the focus of the remainder of my talk is actually going to be on the backhaul network. So we require high throughput backhaul connectivity between the balloons and the mobile network operator's core network on the ground. As with satellite networks, the long distances and high data rates that we want to achieve necessitate the use of very focused energy beams in our data plane. For this, Loon chose to use E-band radios using highly directional steerable antennas to form point-to-point links. So using these links, balloons could connect to ground stations, which had reliable wired connections, as well as to other balloons to form a dynamic moving mesh. So next I want to tell you just a little bit about some of the challenges of trying to make a network with moving nodes and highly directional beams. So for our commercial deployment in Kenya, we sought to expand our coverage for our partner network to an unserved region of about 40,000 kilometers. For reference, this is about the size of Switzerland. So Loon's service objective was to maximize the duration and the area of our 4G service provided to customers on the ground. And then to enable this, our backhaul network's objective was to maximize the connection duration and the throughput of the balloons that had the appropriate conditions to serve users. So in this figure, I'm showing what a good day for us looked like. The green lines show E-band links between balloons, and the green circles show areas with active LTE service on the ground. So a few things to note here. The balloons are nicely distributed throughout the area, so we're getting broad coverage for our service region. And in addition, the backhaul network is a densely connected mesh with multiple redundant paths to the ground. So next, let's take a look at our actual payloads on the balloons and the capabilities of each node in the network. So each balloon carried a communications payload that consisted of multiple LTE antennas and a base station, along with 3 E-band radio transceivers on a steerable gimbal. These were mounted on the bottom corners of the payload of the balloon's bus, and they could articulate as you kind of see in the illustration down at the bottom. In order to establish a backhaul link, the 2 participating radios of the link need to be configured with both radio channel and frequency information, as well as 3-dimensional pointing vectors that allow the transceivers to align with one another. This allows the transceivers to discover one another and lock on to form a link. So creating a link was particularly difficult, often taking multiple minutes at a time to establish a link, and only succeeding about 65% of the time. Now, this is due to the long distances involved between the balloons. These balloons were moving in 3 dimensions, and then objects both on the balloon and in the physical environment could obstruct our radio beams. In addition to that, moisture in the atmosphere, either due to rain, clouds, or fog, could attenuate our signal and degrade performance. And so just for reference, to kind of put perspective on this, the accuracy that we need between these balloons is something equivalent to taking a laser pointer and shining it across the football field and trying to illuminate an apple, and then keeping that apple illuminated for extended periods of time. But the distances we're talking about here are more akin to trying to shine that laser pointer from, let's say, Amsterdam to Frankfurt, or from Los Angeles to Las Vegas. The next challenge after you start thinking about establishing links is choosing which links should be formed. Ideally, we'd like to choose links that would bring maximum utility to the mesh, both in terms of capacity and redundancy and longevity of the network. However, this ends up being a challenging problem because the number of candidate links you have to consider scales with the square of the number of nodes in the sky. For our commercial deployments in Kenya, we only had dozens of balloons, but we anticipated scaling more than 100x as we added additional service regions. Further, the throughput and viability of each candidate link fluctuates over time. This is due to changes in the weather, changes in the distance between our balloons, and the presence of obstructions in the environment. So the graph here shows the set of viable candidate links and its churn over time. You can see here that at medium, about 13% of our candidate links were changing per hour. And before I noted, we didn't actually have enough power to last through the night. And so that actually means that all of our candidate links would turn over daily. And this means that bootstrapping new nodes into the network became extremely important and pretty common. And just as an analogy, think about if you had your own data center or WAN that had a constantly changing topology, and you had to rewire it with a different topology every day. And finally, our system had to weigh the cost of establishing a link versus the cost of tearing one down and trying to form a new, perhaps higher utility link, where that new link may be slow to form and may not form at all. Now, I'd like to note just quickly that these challenges are not only unique to Loon, and may occur to varying degrees in other sorts of networks that have moving nodes and steerable beams. such as satellite communications networks in low Earth orbit, medium Earth orbit, airborne networks, maritime networks, and even newer radio access networks such as 5G, where you have directional beams that are trying to move with moving users. So next, let me tell you a bit about Loon's approach to solving some of these problems, which is our Temporal Spatial SDN. So Loon pioneered the use of this Temporal Spatial SDN approach, which is primarily characterized by its ability to model a changing physical environment in real time and to use predictions from this to model and orchestrate the network. Traditional SDNs are configured with are used to configure current policy of network nodes at layers 3 and above, typically using static models of network topology. In contrast, our Temporal Spatial SDN has a dynamic network model that's influenced by the motion of nodes, the properties of antennas, changing RF propagation environments, etc. It configures both the physical layer, the link layer, and above, and it optimizes the topology to suit the routing objectives. And finally, it focuses not only on the current configuration of the network, but also on future states of the network, and attempts to maximize the network utility over time. So next, let's look at how the TS-SDN idea integrated into Loon's network architecture. So our TS-SDN was deployed in a data center, and it needed to connect with the balloons. So we maintained connectivity from the balloons using 2 commercial satellite communications providers. These channels were originally provisioned primarily as a high priority channel for low data rate flight control operations. These are safety critical operations where we always need to have contact with the balloon. When the network controllers were not, or the flight controllers were not using the network operations team was able to utilize available transmission slots to communicate with the communications payload. These channels were particularly low performance. So we could only transmit a single message at a time, so about 1 kilobyte in flight at any given time with about 1 to 2 minutes of propagation delay. So using the satellite communication channels, the TS-SDN would send radio configuration and antenna pointing commands to the balloons so a balloon could bootstrap and join the mesh. From there, once connected, a high-performance in-band control channel was established, and it was routed using a mobile ad hoc networking routing protocol. And then using this high bandwidth in-band connection, the TS-SDN could then program the data plane, enabling connectivity from the LTE eNode B on the payload back to the mobile network operator's core network. You can find many more details about this architecture in the paper. Okay. Oops, there you go. All right, and now let's take a bit more of a deep dive of how Loon implemented our TS-SDN, which we called Minkowski. So first of all, Minkowski composed of a physical model that was evaluated using weather, motion, antenna, radio characteristics, and RF constraints as inputs. And ultimately, this generates a candidate graph of all the links we could potentially create, both now and at different points in the future. From this, we feed this into a solver, which combines logical network elements about connectivity that we desire, along with historical network states and requests from applications like the LTE stack, to create network intents with both a time dimension for radio resources, links, routes, and tunnels. From here, we compile these intents and actuate them using 2 additional components, which translates the intent into control messages sent off to the balloons via the best control channel we have available. And then the configured state of the balloon is reported back to our actuation layer and recorded by Minkowski both for its own operation and for later debugging. So Minkowski allowed Loon to anticipate link failures and to take steps to quickly recover from them. You can see in this graph the difference between when we could proactively detect that the link was about to fail versus when it unexpectedly failed on us. Remember, links could take minutes to form, especially when commands were transmitted through the satellite network, and so purely reacting to failures was very expensive for us. In addition to anticipating failures, Minkowski allowed us to frequently construct meshes with high-quality links and with good mesh redundancy. And these were actually crucial because when we were able to quickly recover the network due to failures, over 90% of these fast recoveries used redundant links in the network. I should also note that our physical models were far from perfect. About 50% of the links still failed unexpectedly. As predictive models will never be perfectly accurate, reactive recovery mechanisms are always needed in these sorts of systems. And so given the high cost of bootstrapping the nodes via SATCOM and a 50% prediction rate of actually getting it right, this did actually make a meaningful difference in our network, and it improved things substantially. All right, so the TS-SDN approach of Loon's network also improved the big picture as well. So this graph here, I showed the availability of different layers of the network. The blue line is the aggregated per link availability. So essentially this is what percentage of the time do the links that we want to have there actually exist. And then the red line shows our ability to actually use our man-A network over in-band to connect to our control plane. At first glance, you might think that an in-band control plane over an in-band network requires multiple simultaneous connections of our links, and so that our control plane should have lower availability than our links. But you can see in December of 2020 that we actually invert, and this is largely due to additional redundancy that got added as an objective to our solving function. And we expect with more optimizations, our data plane performance to actually improve to surpass our link availability as well. All right, I have 1 more minute, so I will move quickly through a few lessons we learned about modeling the physical environment. So we spent a lot of time trying to model the physical environment well, the RF environment in particular, real-time balloon information, multiple sources of weather data. Ultimately, we found that our predictions were pretty much always wrong, and so I think that the main conclusion would be here that the TS-SDN actually had to be aware of when the physical model was wrong, and it had to be able to adapt to that. And this is one of the control loops that we intended to build and never did, and actually suffered because of it. Right, I guess a few other things to note here. The error that I show in the model is certainly off-shifted, and it was certainly not close to 0 very much of the time. And so I think assuming error in the network and adapting is important. And I probably don't have time to talk about this, but I will say just briefly. Using network telemetry and then overlaying it is actually gives you a great sensing tool to discover when your physical environment is changing. So in this case, we essentially overlaid pointing vectors from a ground station over areas where our links started succeeding and failing. And we were able to discover a number of interesting things, like when we had improper models that tried to point beams through hills or point beams through structures. And then when we had unexpected failures, we actually were able to discover that our physical environment had changed and people had built new buildings that were then obstructing our beams. So network telemetry ends up being very useful and helpful in actually discovering when your physical environment is changing. All right, so I'm well over time. I think that hopefully I've taken a few key ideas away, that we were able to build a network that was improved above the sum of its parts, even using imperfect models. And the network telemetry offered some interesting insights and abilities to improve both our physical models, and our physical models have added the ability to improve our network as well. You can find a bunch more information in our paper. There's actually a large amount of public information about Loon now available on X's website, and we have some open data sets from our network that we'd be very happy for folks to use to further this kind of research. So thank you, and I'll take questions.
Quick question on, you said that your energy didn't last throughout. Was there a way to modulate consumption of energy so that you could say, well, let me use the link less often or something like that to be able to last through the night?
Yes, yeah, definitely. So we certainly had a lot of telemetry on the energy systems of the balloons. I think the main constraint there was we wanted to always make sure that we had enough energy in reserve to operate safety-critical flight systems. And the communications payload was just a lower priority. And so, yeah, there were certain times when we'd say, like, hey, we're about to run out of energy. Let's tear down the mesh, or let's withdraw some links proactively around the balloon, because we knew that was going to go offline soon.
I have a question. So when you want to cover a very huge area using this balloon technology, did you also explore using peer-to-peer balloon architecture? And have you seen any reduction in connection time or the reduction in the number of failures in that case?
Using terrestrial antennas, you're saying. So using terrestrial antennas for backhaul is certainly a possibility. You still need to have reliable power, and you need to have position in order for this to work. I think those things were challenging in a lot of environments that we were trying to operate in. Yeah, I think I'd be happy to talk more about like some of the trade-offs involved there. There are many trade-offs.
Sure, thank you.
All right, I'm also happy to chat with folks offline as well.
Okay. We only have time for one last question. We're already going to be running 10 minutes late in this session, so one last question. Yeah.
Thank you for a good talk. And I have a question in the using satellite as just a control plane, because I guess that both using satellite as a data plane and control plane can be visible. And why did not choose that way?
Yeah, so this is an excellent question, which is a long topic that I won't have time to talk at length about here. So back in 2011, when we started this project, a lot of the low Earth orbit satellites that are being proposed now, were not yet being conceived or existing in any meaningful way. And so I think there's actually a number of trade-offs there that you get with satellite and data plane. One of the nice things about being in the stratosphere is we can still go direct to handset. We're about an order of magnitude lower in the atmosphere than a low Earth orbit satellite, and so just propagation delay-wise, 4G protocol doesn't allow you to go directly to satellite. Another opportunity you have is being lower down, you have a lot more opportunity for higher bandwidth. You can think about it, part of the name of the game here is signal strength of focused energy. So imagine taking a flashlight and shining it down at the table. The closer you are to the table, the more energy you can concentrate in a small area. So you actually have the opportunity with a lower platform to actually densify your bandwidth in a given area much higher than you can from a satellite.
Okay, let's thank Frank.
Thank you.